On May 10th, 2024, auroras appeared over places that were never supposed to see them. The northern lights stretched across Texas, Florida, parts of Mexico, and even regions far closer to the Sahara than the Arctic. For many people, it was a beautiful spectacle. For solar scientists, it was a warning. Just a few years earlier, experts had predicted that the current solar cycle would be relatively modest. Instead, the sun surged past expectations. By August of 2024, monthly sunspot counts had climbed to levels that forecasts failed to anticipate, and the surprises kept coming. The sun's magnetic poles are currently passing through one of the strangest phases of their cycle, with opposing polarities appearing in the same polar region at the same time. In March of 2025, a spacecraft photographed the sun's poles directly for the first time in human history. Scientists had waited decades for that view, and no one knew exactly what it would reveal. Meanwhile, the strongest solar flare of the current cycle erupted before researchers had even confirmed the sun had reached its maximum. What makes all of this unsettling is not the idea that the sun is dying. It is that the most closely monitored object in the history of science is behaving in ways our best models did not fully predict. At the exact moment when satellites, power grids, navigation systems, and global communications depend on understanding it. Quick favor before we continue. If you find yourself coming back to videos like these, hit subscribe so you don't miss the next one. It makes a bigger difference than you might think. It starts with a star we thought we understood better than anything else in the universe. Before we can understand why recent observations caught scientists off guard, we need to spend a moment with the star itself. We see it every day. We build calendars around it. Its light defines morning and evening, yet the object at the center of our solar system remains far stranger than appearances suggest. The sun is often imagined as a giant ball of fire. It is not. Fire is a chemical reaction, and the sun operates through an entirely different process. What we are looking at is a vast sphere of plasma, a state of matter in which atoms have been stripped apart into charged particles. It spans roughly 1,390,000 kilometers, which is about 864,000 miles, across and contains approximately 99.86% of all the mass in the solar system. Deep within its center, hydrogen nuclei are forced together by immense pressure. When those nuclei combine, they form helium and release energy. This process is called nuclear fusion. In simple terms, tiny particles merge into larger ones, and a small amount of mass becomes energy. The journey of that energy is surprisingly slow. A particle of light created near the core may spend anywhere from 10,000 to 170,000 years working its way outward through the dense interior. It bounces endlessly through crowded layers of plasma before finally reaching the surface. Once free, the same light crosses the gulf to Earth in only 8 minutes and 20 seconds. What we call the sun's surface is merely the beginning of its atmosphere. The visible layer is known as the photosphere. Above it lies the chromosphere. Far beyond both extends the corona, a diffuse outer atmosphere revealed most clearly during total solar eclipses. Here we encounter one of solar science's oldest puzzles. The photosphere reaches roughly 5,500 degrees Celsius, or 9,932 degrees Fahrenheit. Yet the corona above it can exceed 1 million degrees Celsius, or 1,800,000 degrees Fahrenheit. Somehow the outer atmosphere becomes dramatically hotter than the layer beneath it. No complete explanation exists. Beneath all of these features lies the mechanism driving the sun's behavior. Unlike Earth, the sun is not solid. Different latitudes rotate at different speeds. Regions near the equator complete rotations faster than regions closer to the poles. Over years, this differential rotation twists and stretches magnetic fields into increasingly complex shapes. That tension eventually emerges at the surface. Sunspots form where concentrated magnetic fields interfere with the normal upward flow of energy. They appear darker than surrounding regions because they are cooler, though still extraordinarily hot. As magnetic stress accumulates and releases, solar activity rises and falls in a repeating rhythm lasting about 11 years. Since 1755, scientists have tracked this cycle continuously. We now live within solar cycle 25, but this pattern is far more than a scientific curiosity. Every satellite, every global positioning system receiver, every radio network, and every major power grid operates within the magnetic influence of this star. The sun is not merely above us, it remains woven into the infrastructure of modern civilization. Before the cycle acquired a number, before charts began bending upward in unexpected ways, a group of researchers gathered around a familiar task. Forecasting the next solar cycle had become a well established scientific exercise. Patterns from previous decades provided guidance. Measurements existed, models existed, historical comparisons existed. By late 2019, confidence was strong enough for an official prediction. The panel had been convened by the National Aeronautics and Space Administration, the National Oceanic and Atmospheric Administration, and the International Space Environment Services. Their conclusion pointed toward a relatively modest cycle. Activity was expected to rise gradually, reach a maximum around July of 2025, and peak near 115 sunspots. The forecast resembled the previous cycle, which had been among the weakest seen in roughly a century. The reasoning appeared sound. Scientists had long observed a relationship between one cycle and the next. During solar minimum, when activity falls to its lowest levels, researchers examine the strength of the sun's polar magnetic fields. These polar fields often act as seeds for the following cycle. Stronger fields generally suggest a stronger future maximum. We had seen this relationship hold repeatedly across decades of observations. Yet nature rarely signs contracts. As the new cycle began unfolding, small discrepancies appeared. During 2021 and 2022, sunspot counts consistently ran ahead of expectations. The difference was not dramatic at first. A few points above the forecast curve can be dismissed as ordinary variation, but the trend persisted month after month. Something was developing beneath the surface. By June of 2023, several solar physicists publicly acknowledged that the cycle was progressing faster than predicted. That admission carried weight. Forecast models are built carefully, and revisions are not made lightly. Still, the data demanded attention. A few months later, the National Oceanic and Atmospheric Administration issued an updated outlook. The expected peak was raised substantially, now projected to fall somewhere between 137 and 173 sunspots. Even this revision represented a major departure from the original forecast, but the sun continued climbing. Through early 2024, activity remained elevated. New active regions emerged. Sunspot groups multiplied. Then, in August of 2024, the monthly sunspot count reached 216. It was the highest monthly value recorded in more than 2 decades, far beyond the original prediction and comfortably above the revised estimate as well. The numbers spoke clearly. Lisa Upton, co-chair of the Solar Cycle Prediction Panel, later remarked that solar activity had slightly exceeded expectations. The phrase became memorable precisely because of its restraint. The gap between prediction and reality had become impossible to ignore. What failed was not scientific diligence. The observations were real, the methods were grounded, and the reasoning followed established evidence. But the sun emerges from interacting magnetic processes so intricate that important details remain beyond our predictive reach. We can measure, compare, and model. We can identify trends and probabilities. Yet the star at the center of our system still retains an element of unpredictability, moving according to rhythms that do not always align with the schedules we create for it. Long before spacecraft, magnetic maps, or modern observatories, people noticed that the sun was not always uniform. Ancient Chinese astronomers recorded dark markings crossing its bright disk as early as around 800 years before the Common Era. These observations were made with the naked eye under particular atmospheric conditions, revealing brief hints that the star overhead possessed changing features of its own. Centuries later, a new tool transformed those observations. In 1610, Galileo Galilei began making systematic telescopic studies of these dark regions. By tracking their movement across the solar surface, he demonstrated that the sun rotates. The discovery carried enormous significance. The heavens were no longer viewed as perfectly unchanging. Motion existed there too. What exactly were those dark patches? A sunspot forms where concentrated magnetic fields break through the visible solar surface, known as the photosphere. In these regions, the normal upward transport of hot plasma is partially suppressed. Plasma, the electrically charged state of matter that dominates the sun, cannot circulate as freely there. Less heat reaches the surface. The result becomes visible. A sunspot appears darker than its surroundings because it is cooler. Yet cooler on the sun remains astonishingly hot by earthly standards. Typical sunspots reach about 3,500 degrees Celsius or 6,332 degrees Fahrenheit. The surrounding photosphere sits near 5,500 degrees Celsius or 9,932 degrees Fahrenheit. The contrast creates the dark appearance that observers detect from afar. Most sunspots do not appear alone. They commonly emerge in pairs or larger groups. Each member carries an opposite magnetic polarity, resembling the two ends of a magnet emerging through the solar surface. Invisible magnetic structures connect them across vast distances. We cannot see those magnetic lines directly, yet their influence shapes everything around them. Some become immense. The largest sunspot groups can exceed Earth's diameter several times over. During the current cycle, one especially complex region attracted considerable attention. The active region, known as 3842, generated the powerful flare released in October of 2024. Its magnetic structure ranked among the most tangled configurations observed during the cycle. Careful observers noticed another detail centuries ago. In 1769, the Scottish astronomer Alexander Wilson found that sunspots appeared slightly sunken when viewed near the sun's edge. This phenomenon, now called the Wilson effect, revealed that sunspots are depressed regions rather than flat stains on the surface. They resemble broad, shallow bowls embedded within the photosphere. But individual sunspots tell only part of the story. As a solar cycle progresses, new groups emerge progressively closer to the equator. This migration pattern became known as Sporer's law, named after the German astronomer Gustav Sporer. When generations of observations are plotted together, the drifting bands create a striking shape called the butterfly diagram. Delicate wings spread across decades of data. Within that pattern, you and we can watch the pulse of the solar cycle unfold, traced entirely through the appearance and movement of sunspots. There comes a stage in every solar cycle when the underlying tension reaches its greatest complexity. Magnetic structures that spent years stretching, twisting, and accumulating energy approach a turning point. Solar physicists call this phase solar maximum. It marks the period when sunspot numbers reach their highest levels, magnetic activity becomes most intense, and the sun's magnetic poles begin exchanging identities. Everything grows busier. The process unfolds across an approximately 11-year rhythm. For years, magnetic fields become increasingly tangled through the sun's uneven rotation. By the time maximum arrives, that stored complexity can no longer maintain its previous arrangement. Large magnetic structures begin breaking apart and reconnecting in new configurations. The entire star enters a period of heightened activity. During the current cycle, an important announcement arrived on October 15th, 2024. The National Aeronautics and Space Administration and the National Oceanic and Atmospheric Administration officially declared that solar cycle 25 had reached solar maximum. Yet the statement included an unusual qualification. Scientists could not identify the peak as it happened. Solar maximum cannot be measured in real time. Instead, researchers examine monthly sunspot counts and smooth the data by averaging values across months before and after a potential peak. Specifically, 6 months on either side are included in the calculation. Only after enough observations accumulate can the highest point be confirmed with confidence. That creates a fascinating situation. By the time the announcement was made, evidence suggested the most active phase may already have occurred. We had been living through the cycle's peak while the final verdict remained uncertain. The sun had already expressed much of its activity before scientists could formally label the moment. Meanwhile, conditions across the solar surface reflected this transition. Sunspot regions became more numerous. Powerful flares appeared more frequently. Vast eruptions of magnetized plasma, known as coronal mass ejections, were launched into space in greater numbers. These eruptions can carry billions of tons of material outward from the sun, transporting magnetic fields across the solar system. But solar maximum does not always arrive as a single summit. Some cycles display two separate peaks with a noticeable dip between them. This pattern is known as Gnevishev's gap, named after the Soviet astronomer Mikhail Gnevishev. Rather than following one smooth rise and decline, activity briefly eases before climbing again. Researchers continue examining current observations to determine whether solar cycle 25 belongs to this category. From Earth, the effects become increasingly visible. Radio communications experience more disruptions. Navigation systems based on satellites can suffer reduced accuracy, particularly at higher latitudes. Geomagnetic disturbances become more common. Auroral displays spread farther from the polar regions than usual, appearing in locations where they are rarely seen. For most of the cycle, these effects remain relatively subdued. During maximum, they become harder to ignore. The magnetic heartbeat of the sun reaches its strongest rhythm, and the connection between our world and the star that governs it becomes far more apparent in everyday technology, in Earth's upper atmosphere, and across the skies above us. For many people, the event began with a photograph. A crimson glow appeared above familiar landscapes. City skylines, rural fields, coastlines, and highways suddenly sat beneath colors that seemed misplaced. Across social media, images spread rapidly. People compared locations, checked timestamps, and wondered whether the pictures were real. They were. During the nights of May 10th and May 11th, 2024, Earth encountered the most powerful geomagnetic storm experienced since the Halloween storms of October 2003. A succession of coronal mass ejections, enormous eruptions of magnetized plasma expelled from the Sun, swept through interplanetary space and struck Earth's magnetic environment in close sequence. The impact was substantial. Forecasters classified the disturbance as a geomagnetic storm level 5 event, the highest category on the scale used by the National Oceanic and Atmospheric Administration. Events of this magnitude can disrupt radio communications, interfere with satellites, and create fluctuations within electrical infrastructure. Under severe conditions, complete radio blackouts may occur across portions of the sunlit side of Earth. Yet the most visible effect appeared overhead. Auroras expanded far beyond their usual territory. Across Europe and North America, observers looked upward and found luminous curtains stretching across the sky. The displays reached northern Mexico, parts of the Caribbean, and even the Sahara Desert. In the United Kingdom, the lights became visible from London. Within the United States, sightings extended into Florida and Texas. Many witnesses had never seen anything similar. Descriptions often focused on deep red and purple hues. These colors appeared because portions of the aurora formed at unusually high altitudes. There, oxygen atoms emitted red light rather than the green glow most commonly associated with auroral displays. Some of these emissions occurred between 200 kilometers, which is about 124 miles, and 300 kilometers, which is about 186 miles, above Earth's surface. The chain of events began days earlier, on the Sunday. Several active sunspot regions produced multiple powerful flares in rapid succession. These eruptions accelerated large numbers of charged particles into space, creating what scientists call a solar energetic particle event. In simple terms, high-energy particles raced outward through the solar system. As one coronal mass ejection cleared material from the path ahead, later eruptions encountered less resistance. They traveled faster. Their impacts intensified. Historical comparisons quickly emerged. The last geomagnetic storm of comparable visibility occurred during the Halloween storms of 2003. The previous occasion when auroras reached much of the southern United States came during the Bastille Day event of July 2000. Yet even those storms remain smaller reference points beside the Carrington event of 1859, which still occupies a category of its own. But statistics tell only part of the story. Farmers across the American Midwest photographed red skies above fields and barns, uncertain at first what they were witnessing. Meteorologists answered questions throughout the night. Astronomers explained the phenomenon to audiences far larger than usual. Thousands upon thousands of images appeared within hours. For a brief period, a process unfolding 150 million kilometers away, which is about 93 million miles away, became visible in the lives of people across much of the planet. On the morning of September 1st, 1859, an astronomer sat at his telescope performing a routine task. Richard Carrington was observing a large sunspot group from his private observatory in Red Hill, Surrey. He carefully sketched the dark structures crossing the solar surface, documenting details much as astronomers had done for generations. Then something extraordinary appeared. Two intensely bright patches erupted within the sunspot region. Carrington watched as the light rapidly intensified and changed shape. No one had ever recorded such an event directly before. Today we recognize it as a white light solar flare, a flare bright enough to be seen in visible light rather than only through specialized instruments. The observation lasted only minutes. its consequences traveled much farther. Within roughly 17 hours, an enormous coronal mass ejection reached Earth. That journey was astonishingly fast. Most such eruptions require between 2 and 4 days to cross the distance, separating Earth from the Sunday. This one arrived with remarkable speed, carrying a powerful magnetic disturbance directly into Earth's magnetic environment. What followed entered scientific history. The resulting geomagnetic storm remains the strongest event documented during the modern observational era. Estimates suggest the smoothed level of solar activity associated with the event reached roughly twice the peak activity observed during solar cycle 25. Even today, researchers continue using it as the benchmark against which all major solar storms are measured. The technological world of 1859 was very different from ours. Electricity existed, though only in limited forms. Telegraph networks represented one of humanity's most advanced communication systems. When the storm arrived, those networks experienced effects that seemed almost impossible. Telegraph wires sparked, equipment caught fire, operators received electrical shocks while attempting to send messages. Some systems behaved even more strangely. Reports described telegraph stations continuing to transmit messages after their batteries had been disconnected. Geomagnetically induced currents, electrical currents generated by disturbances in Earth's magnetic field, flowed through the wires and temporarily powered the systems themselves. The skies reflected the disturbance as well. Auroras spread across vast portions of the planet. Sightings were reported from Cuba, Colombia, and Hawaii. In Europe, observers recorded displays as far south as Rome. Witnesses described skies glowing brightly enough to illuminate newspapers at midnight. Many people reportedly began preparing for sunrise, unaware that the light came from Earth's upper atmosphere. But the event carries a different meaning today. Modern civilization depends upon electrical grids, satellites, navigation networks, communication systems, and interconnected infrastructure operating continuously across enormous distances. A study published by Lloyds of London in 2013 estimated that a modern recurrence could produce damage ranging from $600 billion to $2,600 billion within the United States alone. High voltage transformers would represent a particular vulnerability, and replacing damaged units can require many months or even years. Yet Carrington's storm may not represent the upper limit. Studies of ancient tree rings and polar ice have revealed evidence for even larger solar particle events in 774 and 993. These discoveries, known as Miyake events, suggest eruptions perhaps 10 to 100 times more energetic than the Carrington event itself. The sun has left traces of powers beyond anything humanity has directly witnessed with modern instruments. Imagine standing beside a lake, just as tension within the water suddenly releases. Waves spread outward in every direction. A solar flare begins with a similar release of stored energy, though on a scale far beyond anything familiar on Earth. At its core, a solar flare is an intense burst of electromagnetic radiation. Most of that energy emerges as powerful X-rays and extreme ultraviolet light. The source is a process known as magnetic reconnection. In simple terms, magnetic field lines become twisted and compressed until they abruptly break apart and reconnect into a new arrangement. When that happens, enormous amounts of stored energy are released almost instantly. The event unfolds rapidly. Scientists classify flares according to a logarithmic scale. A logarithmic scale means each step represents a multiplication rather than a simple increase. The categories progress from A to B to C to M, and finally X. Each level carries roughly 10 times more energy than the one before it. Within each category, additional numbers indicate relative strength. An X-class flare rated 9 is approximately 9 times more energetic than an X-class flare rated 1. During October of 2024, the current cycle produced its most powerful flare to that date. Classified as an X-class flare rated 9, it generated a complete radio blackout across portions of Europe, Africa, and the Middle East for roughly 1 hour. Communications relying on high-frequency radio signals were temporarily disrupted as intense radiation interacted with Earth's upper atmosphere. But a flare and a coronal mass ejection are not the same thing. The distinction matters. A solar flare consists primarily of radiation. Because radiation travels at the speed of light, its effects reach Earth in roughly 8 minutes. A coronal mass ejection is different. It is a physical eruption of plasma and magnetic field launched into space. These eruptions travel far more slowly, typically moving between 500 kilometers per second, which is about 311 miles per second, and 3,000 kilometers per second, which is about 1,864 miles per second. Their journey to Earth usually requires between 1 and 4 days. Another hazard arrives in between. Major eruptions can accelerate charged particles to extraordinary velocities. These particles, mainly protons and electrons, form what scientists call solar energetic particles. They can approach the speed of light and race ahead of the larger eruption. When they encounter spacecraft, they may penetrate electronics and increase radiation exposure for astronauts long before the main disturbance arrives. The most powerful flares tend to emerge from especially tangled regions of solar magnetism. Researchers identify these locations by studying magnetic complexity. Areas containing tightly packed fields of opposing polarity are considered particularly dangerous because they hold large amounts of stored magnetic energy waiting for release. Yet, despite decades of observation, one limitation remains. Scientists can identify regions that appear capable of producing major flares. They can estimate probabilities. They can monitor warning signs, but no one can specify the exact moment when a flare will erupt. The trigger remains hidden within magnetic processes that are still only partly understood, one of the enduring challenges at the heart of solar physics. There was a remarkable irony at the center of solar science. Humanity had mapped sunspots, tracked flares, measured solar winds, and monitored magnetic cycles for generations. Yet one of the most important regions of the Sun remained largely unseen. The poles were the missing piece. Every major planet travels around the Sun within roughly the same flattened orbital plane. Spacecraft generally follow that geometry as well. Telescopes on Earth share the same limitation. As a result, nearly every observation of the Sun has come from an angle close to its equator. We could glimpse the polar regions only from the side, never from above. The view was incomplete. For decades, scientists knew those distant polar areas played a crucial role in shaping future solar activity. Yet, direct observations remained unavailable. It was rather like studying Earth's climate while never seeing the Arctic or Antarctic. One mission came close. Between 1990 and 2009, a spacecraft named Ulysses completed 3 journeys over the Sun's poles. Developed through cooperation between the National Aeronautics and Space Administration and the European Space Agency, it gathered valuable measurements of magnetic fields and solar wind conditions. But Ulysses carried no cameras. Its passes produced streams of instrument data rather than photographs. The poles remained unseen. That absence mattered greatly because the sun's polar magnetic field serves as the starting point for the next solar cycle. During solar minimum, scientists measure the strength of these polar fields and use them to estimate future activity. As recent events demonstrated, those forecasts remain imperfect. Even so, understanding how magnetic fields evolve near the poles is fundamental to understanding the larger cycle itself. A new mission was designed specifically to address that gap. The spacecraft Solar Orbiter, launched in February of 2020, built by the European Space Agency with contributions from the National Aeronautics and Space Administration, it carried 10 scientific instruments. Some could photograph the sun directly. Others measured magnetic fields, particles, temperatures, and chemical signatures. For the first time, a mission possessed the ability to both observe and analyze the poles simultaneously. Reaching the correct vantage point required patience. Solar Orbiter repeatedly used gravity assists from Venus. A gravity assist is a maneuver in which a spacecraft borrows momentum from a planet to alter its path. With each encounter, the spacecraft increased its orbital inclination, meaning the angle of its orbit relative to the planetary plane. By March of 2025, it had reached 17 degrees. By December of 2026, 24 degrees. By June of 2029, 33 degrees. Then history arrived. On March 22, 2025, Solar Orbiter obtained humanity's first direct view of the Sun's south pole. The moment represented the beginning of an entirely new observational era. Sami Solanki of the Max Planck Institute for Solar System Research, who leads the mission's magnetometer investigation, captured the significance of the achievement. He explained that scientists did not know exactly what to expect from the first observations because the poles were, in his words, literally unknown territory. For generations, solar science had worked around a blind spot. At last, that blind spot began to disappear. When the first polar data arrived, scientists were not looking at a stable magnetic cap perched neatly atop the sundae. Instead, they found turbulence. The South Pole appeared remarkably disordered. Maps produced by Solar Orbiter revealed magnetic regions carrying opposite polarities tangled together across the same polar territory. Areas behaving like magnetic north existed beside areas behaving like magnetic south. Rather than a single dominant polarity controlling the pole, a patchwork of competing magnetic structures occupied the region simultaneously. This was not unexpected, yet it had never been observed directly before. The explanation lies within the cycle itself. During the years surrounding solar maximum, the sun's global magnetic field undergoes a reversal. The organized magnetic configuration established during quieter phases gradually breaks apart. Before a new polarity can fully take hold, the old structure dissolves into a transitional state. Order gives way to complexity. The pole enters a period of magnetic confusion before a new arrangement eventually emerges. Solar Orbiter arrived at precisely the right moment. For the first time, humanity was watching the reversal as it unfolded, rather than reconstructing it afterward through indirect measurements. Processes that had existed largely within theoretical models were suddenly visible. One of the mission's most important instruments was the polarimetric and helioseismic imager. This instrument measured magnetic fields at the solar surface with unprecedented precision at high latitudes. The results revealed magnetic field lines drifting toward the poles at speeds between 10 meters per second and 20 meters per second. Those values closely resembled measurements from lower solar latitudes. That finding mattered. Several models had suggested substantially different behavior near the poles. Instead, the observed flows appeared more familiar than expected, providing researchers with new constraints on how magnetic material circulates through the Sunday. Another instrument opened an entirely different window. The spectral imaging of the coronal environment instrument produced Doppler velocity maps from polar regions for the first time. A Doppler map measures motion by detecting tiny shifts in light caused by movement toward or away from an observer. These observations tracked the behavior of charged particles at high latitudes and provided fresh clues about where the solar wind begins and how it escapes into space. Above the pole, the extreme ultraviolet imager captured structures within plasma heated to millions of degrees Celsius or millions of degrees Fahrenheit. From this unusual perspective, the outer atmosphere revealed patterns that had never been photographed from such an angle. But perhaps one of the most intriguing discoveries involved structures known as supergranules. These are enormous convective cells within solar plasma. Researcher Lakshmi Pradeep Chitta explained that the cells function as natural tracers, making the sun's large-scale circulation visible. For the first time, scientists could directly observe magnetic material flowing from equatorial regions toward the poles, a circulation pattern that drives the familiar 11-year cycle. The significance extended beyond any single observation. Professor Carol Mundell, Director of Science for the European Space Agency, described the achievement as humanity's first ever view of the sun's poles and the beginning of a new era in solar science. After generations of studying a star from the side, we had finally begun looking over the edge. A compass on Earth points toward a magnetic pole that drifts slowly over time. The sun possesses magnetic poles as well, yet, unlike Earth's, they do something far more dramatic. They exchange places. This reversal happens during every solar maximum. The sun's large-scale magnetic field, often described as a magnetic dipole because it resembles a giant bar magnet with two opposing poles, gradually transforms until magnetic north becomes magnetic south and magnetic south becomes magnetic north. It is one of the most fundamental processes governing solar behavior. Yet the change is never abrupt. Months pass as the transition unfolds. One pole may begin reversing before the other. The process progresses unevenly across the solar surface before eventually reaching completion. During solar cycle 25, observations indicate that the reversal occurred over a period extending roughly from August of 2024 through January of 2025. Behind this transformation lies a mechanism first described by American astronomers Horace Babcock and Robert Layton. The Babcock-Layton mechanism begins with sunspots. As sunspot pairs emerge, they are usually tilted slightly relative to the solar equator. Each member of a pair carries opposite magnetic polarity. Over time, magnetic material from these regions disperses across the surface. Some of it drifts toward the poles. There, the incoming magnetic flux gradually cancels the older polar field. As more flux arrives, a new field begins forming with the opposite orientation. The process resembles renewal through accumulation. Individual sunspot groups appear and disappear. Their magnetic remnants continue traveling. Collectively, they reshape the entire global field. Another discovery revealed an even deeper pattern. In 1908, George Ellery Hale found that sunspot pairs obey a remarkably strict magnetic rule. Within a given cycle, sunspots leading the direction of rotation carry one polarity in the northern hemisphere and the opposite polarity in the southern hemisphere. During the next cycle, the arrangement reverses. This pattern became known as Hale's Law. Its implications are profound. The familiar 11-year cycle tracks changes in activity levels, but the complete magnetic cycle requires two of those periods. Only after two reversals does the magnetic configuration return to its original state. The true magnetic rhythm of the Sun therefore spans approximately 22 years. Scientists call this longer pattern the Hale cycle. But during the reversal itself, magnetic order temporarily dissolves. Observations from the polarimetric and helioseismic imager aboard Solar Orbiter revealed that the South Pole in early 2025 lacked a dominant polarity altogether. Regions of opposing magnetic orientation existed in near balance. This rare state of magnetic equipoise marks the precise boundary between one magnetic era and the next. For generations, researchers could only infer how new polar fields emerged after such transitions. Now, direct measurements are becoming possible. As Solar Orbiter continues observing the poles, scientists can watch the fresh magnetic field establish itself and measure how rapidly its strength grows. The answer matters because that developing polar field becomes the seed from which solar cycle 26 will eventually emerge. Most rhythms we have explored unfold within a human lifetime. A child can witness several solar maxima. A researcher may spend decades tracking the rise and fall of multiple cycles. But hidden beneath those familiar patterns is a much slower pulse. It moves across generations. Astronomers call it the centennial Gleisberg cycle. Unlike the 11-year cycle that governs the regular waxing and waning of sunspot activity, this longer variation appears to operate across roughly 80 to 100 years. Its influence is subtle. It does not replace the shorter cycle. Instead, it seems to modulate its strength, gradually lifting or lowering the overall intensity of successive generations of solar activity. The idea traces back to 1939. That year, German astronomer Wolfgang Gleisberg examined historical sunspot records extending across many decades. As he studied the data, he noticed a possible long-term oscillation hidden within the familiar cycle pattern. Periods containing several stronger maxima appeared to be followed by intervals marked by generally weaker activity. The changes unfolded so slowly that they could easily escape notice within a single scientific career. The evidence remains imperfect. Unlike the 11-year cycle, which can be directly observed and measured through well-established solar behavior, the centennial Gleisberg cycle emerges primarily through statistical analysis. Scientists have not yet identified a universally accepted physical mechanism driving it. Some researchers debate its precise timing and strength. Others question whether multiple overlapping processes contribute to the pattern. Yet interest persists. The historical signal has proven compelling enough to attract serious scientific investigation for decades. While the cycle lacks the precision of shorter solar rhythms, many researchers consider it too persistent to dismiss entirely. Recent observations have renewed that discussion. Solar cycle 24 ranked among the weakest maxima observed in roughly a century. Expectations for solar cycle 25 reflected that trend. Yet the Sun exceeded those forecasts by a considerable margin. As the cycle strengthened, some researchers began considering whether a larger background shift might be underway. The possibility is intriguing. If the centennial Gleisberg cycle has entered a rising phase, then solar cycles 26 and 27 could also arrive stronger than many baseline forecasts currently assume. Research published in the journal Space Weather during 2025 explored this possibility and suggested that a century scale increase in activity could influence space weather expectations for decades rather than years. But this should not be confused with catastrophe. A stronger background phase does not imply that Carrington scale storms suddenly become common occurrences. The distinction is important. What it may indicate is that the baseline level of solar activity could be higher than recent decades have conditioned us to expect. The last 30 years were shaped by two comparatively weak cycles, and those years may not represent the long-term norm. That possibility is why many solar scientists speak of a new era. The change is not dramatic in a single moment. It unfolds gradually, across decades. Beneath the familiar 11-year rhythm, a slower clock may be turning, carrying the sun toward conditions that few people alive today have ever experienced firsthand. Everything we have observed so far, sunspots, magnetic reversals, flares, and storms, begins far beneath the visible surface. The phenomena that capture our attention are only the outward expressions of processes unfolding deep inside the Sunday, and no one has ever seen them directly. No camera can peer into the solar interior. No spacecraft can descend through its layers. The region responsible for the sun's magnetic behavior remains hidden from view, buried beneath vast depths of plasma. Yet scientists have gradually assembled a picture of this unseen world. At the center lies the core. This is where nuclear fusion occurs. Hydrogen nuclei combine to form helium, releasing enormous amounts of energy. Surrounding the core is the radiative zone. Here, energy travels outward in the form of photons. A photon is a particle of light. Its journey through this region is extraordinarily slow because it is constantly absorbed and re-emitted by surrounding matter. Rather than moving straight outward, the energy follows a long and random path. Farther from the center, conditions change dramatically. The outer third of the sun is known as the convection zone. In this region, hot plasma rises toward the surface, cools, and then sinks again. Vast circulating currents develop. Some convective structures span distances larger than entire planets. The sun becomes a churning ocean of electrically charged gas. But between the radiative zone and the convection zone lies a far more intriguing layer. Solar physicists call it the tachocline. This narrow boundary sits at roughly 70% of the sun's radius measured from the center. It marks the transition between the relatively stable interior below and the turbulent convection above. Many researchers believe this is where the sun's magnetic field is generated and amplified. If the solar cycle has an engine room, the tachocline is its leading candidate. The mechanism driving this process is known as the solar dynamo. A dynamo is a system that converts motion into magnetic energy. Because the sun rotates at different speeds, faster near the equator and slower near the poles, magnetic field lines become stretched and twisted over time. Gradually, fields that once ran north to south become wrapped around the sun in an east to west direction. The magnetic structures strengthen. Eventually, they become buoyant enough to rise through the convection zone and emerge at the surface as sunspot pairs. Yet how do we study a place we cannot see? The answer comes from helioseismology. This technique examines sound waves traveling through the solar interior. Convection generates immense acoustic vibrations that move throughout the Sunday. By measuring tiny oscillations visible at the surface, scientists can infer conditions hidden far below. It is similar to how geologists use earthquake waves to study Earth's interior. Recent analyses have revealed something particularly fascinating. Acoustic signatures associated with solar cycle 26 have already been detected beneath the surface, even though solar cycle 25 has only recently reached its peak. The next cycle is already taking shape within the dynamo. Long before new sunspots appear, the machinery responsible for them has quietly and steadily begun working. Far above the visible surface, the sun fades into a vast outer atmosphere that stretches millions of kilometers into space, which is about hundreds of thousands to millions of miles, depending on the distance measured. This region is known as the corona, and despite decades of study, it remains one of the greatest unsolved mysteries in astrophysics. The puzzle begins with temperature. The photosphere, the visible surface we see from Earth, reaches roughly 5,500 degrees Celsius, or 9,932 degrees Fahrenheit. Common sense suggests that temperatures should decrease as we move farther from the source of heat. Yet the corona behaves very differently. There, temperatures rise to between 1 million and 3 million degrees Celsius, or approximately 1,800,000 and 5,400,000 degrees Fahrenheit. During major flares, some active regions can approach 10 million degrees Celsius or 18 million degrees Fahrenheit. That creates a profound contradiction. Moving away from a heat source should not make a region hotter. Something within the corona is receiving enormous amounts of energy and converting it into heat. The challenge is determining exactly how that happens. Two leading explanations dominate the discussion. The first involves Alfvén waves. These are magnetic disturbances that travel along magnetic field lines, much as vibrations move along a stretched string. Scientists suspect that such waves may carry energy upward from lower layers of the sun and release it into the corona. If enough energy is deposited, the atmosphere can maintain its extraordinary temperatures. The second explanation emerged from a proposal made by physicist Eugene Parker in 1988. He suggested that the corona might be heated by countless tiny magnetic reconnection events. Reconnection occurs when magnetic field lines snap apart and reconnect in a different configuration, releasing energy. Each individual event would be far too small to detect directly. Together, however, they could provide continuous heating. Parker called these hypothetical events nanoflares, but proving their existence has been difficult. Solar Orbiter was designed in part to search for evidence. Its extreme ultraviolet imager began revealing countless miniature brightening events across the solar atmosphere. Researchers nicknamed them campfires. Observations published during 2022 and 2023 showed that these tiny flashes were widespread and energetic. Whether they represent the nanoflares Parker envisioned or a closely related phenomenon remains under investigation. At the same time, another spacecraft was approaching the mystery from a different direction. The Parker Solar Probe, launched in 2018, has traveled closer to the Sun than any mission before it. Its planned closest approach reaches approximately 6,100,000 kilometers from the solar surface, which is about 3,790,000 miles. At that distance, the spacecraft operates within the corona itself. The measurements have been remarkable. During 2023 and 2024, Parker Solar Probe recorded powerful magnetic disturbances known as switchbacks. These events involve sudden reversals in the direction of the solar wind's magnetic field. Some researchers suspect they may be connected to the same energy release processes responsible for heating the corona. The mystery remains unsolved, but for the first time, we are gathering evidence from inside the phenomenon itself. Long before a flare erupts or a magnetic storm reaches Earth, something is already flowing outward from the sun without pause. It never stops. Every second, every day, every year, a vast stream of charged matter expands through space. This is the solar wind. The solar wind consists primarily of protons and electrons escaping from the corona and spreading outward in all directions. These particles travel at remarkable speeds. Depending on their origin, they move between roughly 300 kilometers per second, which is about 186 miles per second, and 800 kilometers per second, which is about 497 miles per second. The idea was once controversial. In 1958, physicist Eugene Parker proposed that the sun's outer atmosphere could not remain static. The corona was simply too hot. According to his calculations, solar material had to expand continuously into space. Many scientists considered the proposal excessively speculative. The journal reviewing his paper initially rejected it. Publication proceeded only after Subramanian Chandrasekhar intervened on Parker's behalf. History soon favored the prediction. Observations from the Soviet spacecraft Luna 1 in 1959 and the American spacecraft Mariner 2 in 1962 confirmed that the solar wind was real. Its reach is immense. The solar wind fills the heliosphere, the enormous bubble-shaped region dominated by solar influence. This structure extends to approximately 100 astronomical units from the Sunday. An astronomical unit is the average distance between Earth and the Sunday. At its outer edge, the pressure of the outward flowing solar wind balances the inward pressure of the interstellar medium, the sparse material that occupies the space between stars. That boundary is known as the heliopause, but the solar wind is not uniform. Scientists generally divide it into two categories. Fast solar wind travels between 600 kilometers per second, which is about 373 miles per second, and 800 kilometers per second, which is about 497 miles per second. It emerges from coronal holes, regions where magnetic field lines open directly into space and allow plasma to escape more easily. The slow solar wind behaves differently. Its speed typically ranges between 300 kilometers per second, which is about 186 miles per second, and 400 kilometers per second, which is about 249 miles per second. Its origin remains less certain. Multiple mechanisms may contribute to its formation. Understanding that process has become one of the major goals of Solar Orbiter and Parker Solar Probe. Here on Earth, we possess substantial protection. Our planet is surrounded by the magnetosphere, a magnetic shield generated by motions within the liquid iron outer core. Most incoming solar wind particles are deflected around this protective barrier. Yet the defense is not complete. Near the poles, magnetic field lines guide some particles downward into the upper atmosphere. There they interact with atmospheric gases and produce auroral displays. But conditions become far more dynamic during solar maximum. The solar wind grows increasingly variable in both speed and density. Coronal mass ejections compress and disturb the surrounding flow. When these disturbances collide with Earth's magnetosphere, powerful geomagnetic storms can develop, creating the same kind of brilliant auroral displays that spread across much of the world during May of 2024. Imagine an invisible structure larger than our planet by many orders of magnitude constantly reshaped by a stream of particles arriving from the Sunday we live inside that structure. Every moment of every day, it surrounds Earth and absorbs the impact of space weather. This is the magnetosphere. Generated by motions within Earth's liquid iron outer core, the magnetosphere forms a protective magnetic bubble around the planet. On the side facing the Sun, it extends roughly 65,000 kilometers, which is about 40,389 miles. On the opposite side, solar wind pressure stretches it into a vast magnetic tail, extending hundreds of thousands of kilometers into space, which is about hundreds of thousands of miles. The result resembles a teardrop carried by an endless cosmic wind. Most of the time, this shield performs remarkably well. Charged particles approaching Earth are redirected around the magnetic boundary, but the protection is not absolute. Certain solar storms arrive carrying a magnetic orientation that can interact directly with Earth's own field. When a coronal mass ejection reaches our planet with a southward pointing magnetic field, it encounters Earth's northward directed magnetic field at the sunward boundary. A remarkable process can then occur. Scientists call it magnetic reconnection. This phenomenon happens when magnetic field lines break apart and reconnect into new configurations, releasing energy in the process. At Earth, reconnection can temporarily create pathways through the magnetic shield. Solar particles gain access to regions they would normally be unable to reach. This is one of the primary drivers of severe geomagnetic storms. Farther inside the magnetosphere, additional structures await. The Van Allen radiation belts form two giant donut-shaped zones of trapped energetic particles. The inner belt begins at roughly 1,000 kilometers above Earth, which is about 621 miles. The outer belt occupies regions near 25,000 kilometers altitude, which is about 15,534 miles. Magnetic forces hold these particles in place, creating a dynamic environment that constantly responds to solar activity. But major storms alter the balance. The belts can swell, intensify, and shift position. Radiation levels rise. Satellites traveling through these regions face increased exposure. This is especially important for spacecraft operating in medium Earth orbit, including many navigation satellites relied upon throughout the modern world. History has already provided a warning. During March of 1989, a geomagnetic storm, far weaker than the Carrington event, triggered severe consequences. Electrical transformers in Quebec suffered damage, and the province experienced a widespread blackout lasting approximately 9 hours. About 6 million people lost electrical power. Today's technological exposure is far greater. Around 1989, roughly 2,000 satellites orbited Earth. By 2024, more than 7,000 satellites were operating in space. Large commercial constellations now occupy low Earth orbit, where geomagnetic storms heat and expand the upper atmosphere. Increased atmospheric drag follows. The effects are measurable. During the geomagnetic storm of May 2024, approximately 40 Starlink satellites encountered elevated drag and were required to perform orbital maneuvers to maintain their trajectories. That storm attracted global attention, yet by historical standards, it was not an extreme event. It simply revealed how closely modern civilization now depends on the strength and limitations of Earth's magnetic shield. A traveler crossing a desert learns to respect the limits of shelter. Beyond a certain distance, protection fades and exposure begins. Space presents a similar boundary, though it is invisible and shaped by magnetic fields rather than landscapes. Astronauts encounter that boundary every day. The International Space Station circles Earth at an altitude of approximately 400 kilometers, which is about 249 miles. At that height, the station remains inside the magnetosphere. Earth's magnetic field still provides significant protection from energetic particles arriving from the Sunday. Yet, the shielding is incomplete. Radiation levels aboard the station remain far higher than those experienced at Earth's surface. Most of the time, the risk is manageable, but major solar energetic particle events can change conditions rapidly. These events involve high-energy protons and electrons accelerated to extraordinary speeds by solar eruptions. When such particles reach near Earth space, astronauts may receive elevated radiation doses within a relatively short period. Preparation is essential. For this reason, astronauts aboard the International Space Station maintain designated radiation shelter areas. These locations are generally chosen because they contain larger concentrations of equipment, supplies, and water. Water is particularly valuable because it absorbs radiation efficiently compared with many other materials available in orbit. During a severe particle event, crew members could gather within these better protected sections while waiting for the most intense phase to pass. But future missions will venture much farther. The Artemis II mission is expected to become the first crewed lunar flight since Apollo 17 traveled beyond Earth orbit in 1972. Unlike astronauts aboard the International Space Station, the crew will leave the magnetosphere behind. Beyond that boundary, exposure to solar radiation increases substantially. The Moon offers little assistance. It possesses no global magnetic field and lacks a substantial atmosphere. During a major solar energetic particle event, astronauts on the lunar surface could face dangerous radiation levels. Space radiation physicist Patricia Rafe has described some potential exposures as approaching nearly lethal doses under extreme conditions. Protection, therefore, becomes a matter of engineering and geography. Astronauts could retreat into spacecraft designed with shielding in mind. Future habitats may be constructed beneath layers of lunar regolith, the loose material covering the Moon's surface. Researchers have also identified lava tubes, naturally formed underground tunnels that could provide substantial protection from radiation and micrometeorites. Mars presents an even greater challenge. A journey to Mars typically requires roughly 6 to 9 months of travel each way. Throughout that voyage, crews would spend long periods in interplanetary space without magnetospheric protection. Upon arrival, they would find only weak, localized crustal magnetic fields rather than a global shield. The planet cannot provide the same level of protection Earth offers. Mission planners attempt to reduce these risks through what is often called an all-clear window. Deep space missions are preferably scheduled during periods of lower solar activity, but the Sun does not always cooperate with forecasts. As recent cycles have demonstrated, significant activity can emerge unexpectedly. Even with increasingly sophisticated observations, certainty remains beyond reach, and every journey beyond Earth's protective field must account for that reality. Not every chapter of the Sun's history has been marked by storms, flares, or abundant sunspots. There have been times when the star at the center of our system seemed to retreat into an unusually subdued state, leaving behind one of the most intriguing mysteries in solar science. The best-known example is the Maunder minimum. This period lasted from approximately 1645 to 1715. It was later named after British astronomers Edward Maunder and Annie Maunder, who carefully examined historical records during the late 19th century and recognized that something extraordinary had occurred. For decades, the familiar rhythm of solar activity appeared to weaken dramatically. The records were striking. Observers who regularly monitored the Sun reported months passing without a single sunspot. In some cases, years elapsed with almost no visible activity. During a typical solar maximum, hundreds or even thousands of sunspots may appear over the course of a cycle. Yet, across the entire 70-year span of the Maunder minimum, the total number of recorded sunspots was comparable to what might normally occur in a single active year. The sun had not turned off. Fusion continued in the core. Energy still flowed outward, but the magnetic processes responsible for generating visible surface activity had entered an unusually suppressed state. At the same time, conditions on Earth were changing. The Maunder minimum coincided with the coldest phase of a broader climatic interval known as the Little Ice Age. Across parts of the northern hemisphere, average temperatures declined noticeably. The River Thames in London froze frequently enough for large frost fairs to be held directly on the ice. Agricultural growing seasons shortened. Harvest failures became more common. In some regions, famine followed. But the relationship remains complex. Researchers continue debating how much of the cooling resulted directly from reduced solar activity and how much stemmed from other influences, including volcanic eruptions and long-term shifts in ocean circulation. Even so, estimates suggest total solar energy output may have declined by roughly 1/10 to 2/10 of 1% during the Maunder minimum. That reduction is generally regarded as a contributing factor. Evidence for similar events extends much farther into the past. Scientists study cosmogenic isotopes, radioactive atoms formed when cosmic rays interact with Earth's atmosphere. Cosmic rays penetrate more easily when solar activity is weak because the sun's magnetic influence provides less shielding. Carbon-14, preserved in tree rings, and beryllium-10, trapped within ancient ice, allow researchers to reconstruct solar behavior across thousands of years. Those records reveal that the Maunder minimum was not unique. Earlier episodes include the Spurrier minimum, spanning approximately 1460 to 1550, and the Wolf minimum, extending from roughly 1280 to 1350. Both indicate prolonged intervals of unusually weak solar activity lasting many decades. These discoveries reshape our perspective. The highly active sun, observed throughout much of the 20th century, may not represent the standard condition of our star. Instead, the historical record suggests that long periods of strength and long periods of weakness are both part of a much larger story, unfolding across centuries beyond the span of any individual lifetime. If we compress centuries of solar history into a single timeline, one period stands apart for its remarkable intensity. Across the second half of the 20th century, the sun displayed a level of activity that now appears unusually elevated when compared with much of the longer historical record. Scientists call this interval the modern maximum. Roughly spanning the years between 1950 and 2000, the modern maximum encompassed several exceptionally active solar cycles. Solar cycles 18 through 22 generated some of the highest sunspot counts and strongest space weather events ever recorded during the era of systematic observations. For researchers studying long-term solar behavior, this period became an important benchmark. One cycle towered above the rest. Solar Cycle 19 reached its peak around 1957 during the International Geophysical Year, a major international scientific effort dedicated to studying Earth and space. The cycle achieved a smoothed sunspot maximum of approximately 201, the highest value recorded in the modern observational record. At the time, it appeared to confirm a trend toward increasingly vigorous solar activity. But the pattern did not continue. The following cycle arrived weaker than many scientists expected. Solar Cycle 20 displayed a substantial decline in activity despite emerging immediately after the strongest cycle ever measured. That abrupt shift puzzled researchers for decades. Traditional models struggled to explain how the sun could move so dramatically from one cycle to the next. A possible answer emerged much later. Research published during July of 2025 employed advanced simulations of magnetic field evolution that incorporated the Babcock-Leighton mechanism. The results suggested that seemingly small variations in the tilt angles of emerging sunspot pairs can produce major differences in future cycle strength. Sunspot pairs rarely emerge in perfectly uniform orientations. Tiny deviations accumulate over time and influence how much magnetic flux ultimately reaches the poles. The implications are profound. These fluctuations arise from the sun's own internal variability. They introduce an element of randomness into the cycle building process. Even if scientists fully understand the underlying dynamo, certain aspects of future activity may remain fundamentally unpredictable. That realization places a natural limit on forecasting. Predictions can improve, models can become more sophisticated, additional observations can reduce uncertainty. Yet the sun may always preserve some degree of inherent unpredictability because part of its future behavior depends upon countless small magnetic variations unfolding beneath the surface. This perspective also reshapes how researchers interpret recent decades. The transition from the highly active modern maximum into the comparatively weak solar cycles 23 and 24 initially suggested that the sun might be entering a prolonged downturn. Then, solar cycle 25 exceeded expectations. That unexpected resurgence prompted renewed interest in longer term patterns, such as the centennial Gleisberg cycle. But perhaps the broader story is not one of anomaly. Researchers are increasingly examining whether the intense activity of the 20th century represented an unusually high peak within a century scale rhythm, or whether it reflected conditions that periodically return throughout solar history. From that perspective, solar cycle 25 may not be a strange exception at all. Instead, it could represent a gradual return to activity levels that become familiar when we widen our view beyond a single lifetime and begin measuring the sun in centuries rather than years. Every day, long before a solar storm reaches Earth, a group of forecasters watches the sun with the same intensity that meteorologists watch developing hurricanes. Their task is not to predict rain or wind. It is to anticipate disturbances arriving from a star nearly 150 million kilometers away, which is about 93 million miles. At the center of that effort is the Space Weather Prediction Center. Located in Boulder, Colorado, the center serves as the operational hub for space weather forecasting in the United States. Its alerts support government agencies, military operations, aviation networks, satellite operators, and power grid managers. When solar activity increases, decisions affecting critical infrastructure often begin with information produced there. The work never stops. Forecasters continuously monitor the sun using a network of spacecraft and instruments. Sunspot regions are evaluated daily according to their magnetic complexity. Areas containing tangled magnetic fields receive special attention because they are more likely to produce major eruptions. At the same time, solar X-ray output is measured by the Geostationary Operational Environmental Satellite Series, providing immediate evidence of flare activity. Additional perspectives come from space. Coronagraph instruments aboard the Solar and Heliospheric Observatory, a joint mission of the National Aeronautics and Space Administration, and the European Space Agency, operating since 1995, create artificial eclipses that reveal coronal mass ejections expanding into space. Observations from the Solar Terrestrial Relations Observatory spacecraft help track those eruptions from different viewing angles, improving estimates of their speed and direction. But one location is especially important. Scientists maintain instruments near the first Lagrange point, a gravitational balance region approximately 1,500,000 kilometers sunward from Earth, which is about 932,000 miles. Spacecraft positioned there continuously sample the solar wind before it reaches our planet. That distance provides a crucial advantage. Fast-moving solar wind and approaching coronal mass ejections can be detected roughly 15 to 60 minutes before arrival at Earth. The warning window is brief, yet extremely valuable. Satellites may be placed into protective configurations. Power grid operators can take precautions to reduce stress on vulnerable systems. Astronauts can move toward shielded areas. Forecasts become increasingly urgent as confidence grows. Space weather watches are issued when conditions suggest a significant geomagnetic storm may develop within the next 1 to 3 days. Warnings follow when arrival becomes imminent. During the major storm of May 10, 2024, a Level 5 geomagnetic storm watch provided several hours of preparation time. Most affected organizations responded effectively, yet forecasting remains extraordinarily difficult. Unlike terrestrial weather, space weather lacks dense observation networks distributed throughout the environment being studied. Scientists can identify active regions and estimate eruption probabilities, but they cannot predict flare timing with useful precision far in advance. One obstacle stands above all others. The most important factor determining whether a coronal mass ejection will strongly affect Earth is the orientation of its magnetic field. That orientation cannot usually be measured until the eruption is nearly upon us. Solving this problem is now a major objective of future missions. Researchers hope that spacecraft positioned near the fourth and fifth Lagrange points may eventually provide earlier measurements, extending the warning time available before the next significant solar storm arrives. Imagine a clock beginning its countdown with no visible sign on the horizon. The forecasts have been issued. Operators have reviewed procedures. Satellites have shifted into protective configurations. Yet the true test of preparedness begins only when a rare event unfolds faster than the systems built to withstand it. Consider one possible scenario. A flare classified at approximately X20 class erupts from an active solar region. Accompanying it is a fast, full halo coronal mass ejection carrying a strongly southward magnetic field. Statistical studies of flare energies suggest events of this scale may occur only once or twice per century. Even so, rarity offers little comfort when the sun directs one toward Earth. The first effects arrive almost immediately. About 8 minutes after the eruption, intense X-rays reach our planet at the speed of light. High-frequency radio communication across the day side of Earth experiences major disruption. Aircraft operating on transpolar routes lose reliable communication links. Air traffic controllers activate contingency procedures. Emergency services in affected regions begin shifting toward backup systems designed for communication outages. But the situation continues to evolve. Roughly 8 hours after the eruption, energetic particles accelerated by the event begin reaching near Earth space. Satellites operating in medium Earth orbit encounter elevated radiation levels. Electronic systems experience increasing rates of bit flips, small errors caused when energetic particles alter stored digital information. Navigation networks become less reliable. Positioning accuracy degrades across large portions of the world, affecting transportation, logistics, agriculture, and timing systems that depend upon precise synchronization. Then comes the largest impact. Between 18 and 24 hours after the eruption, the coronal mass ejection arrives. The collision compresses Earth's magnetic field and triggers an intense geomagnetic storm. Fluctuating magnetic fields generate electrical currents within the ground itself. These geomagnetically induced currents flow through long transmission lines, pipelines, railway tracks, and other extensive conductive structures that unintentionally behave like enormous antennas. Power systems face the greatest danger. High voltage transformers operate near magnetic saturation under normal conditions. Sudden geomagnetically induced currents can push them beyond design limits. Utilities cannot simply disconnect every transformer instantly without risking cascading failures across interconnected grids. Damage to these systems creates a second problem. Many transformers are custom engineered, manufactured in limited quantities, and require long production schedules. Replacement can take between 12 and 18 months. The consequences extend far beyond electricity. A report published by Lloyds of London during 2013 estimated that a Carrington scale event could leave between 20 million and 40 million Americans without power. Outages in the most severely affected regions could persist from 16 days to 1 or 2 years. Economic losses were estimated between 600 billion and 2 trillion 600 billion United States dollars. But the modern world has become even more interconnected since that assessment. There are more satellites overhead, more cloud infrastructure supporting daily activity, and more logistics systems dependent upon global positioning services. Fiber optic networks themselves resist induced currents, yet their repeater stations still require power. The deeper our technological connections become, the more a severe space weather event transforms from a scientific phenomenon into a challenge touching nearly every layer of modern civilization. Long before power grids, satellites, or forecasting centers existed, the relationship between Earth and the Sun was already shaping the conditions that allowed every forest, ocean, and living organism to exist. Beneath the dramatic events we have explored lies a slower connection, one measured not in hours or days, but across seasons, centuries, and geological ages. At the top of Earth's atmosphere, the Sun delivers approximately 1,361 watts of energy per square meter. Scientists call this value the solar constant. Despite its name, it is not perfectly constant. Across a typical 11-year solar cycle, the total solar energy reaching Earth varies by roughly 0.1%. The highest values occur near solar maximum, while the lowest arrive near solar minimum. That change appears remarkably small. Yet Earth is a complex system. Oceans store enormous quantities of heat. Atmospheric circulation redistributes energy across the globe. Chemical reactions unfold at different rates, depending on temperature and sunlight. When solar variability interacts with these systems, measurable regional climate effects can emerge, though researchers continue investigating the precise mechanisms and their relative importance. But total energy tells only part of the story. The sun's ultraviolet output changes far more dramatically than its overall brightness. In certain ultraviolet wavelengths, variations can reach between 6 and 8% during the solar cycle. Ultraviolet radiation drives the production of ozone within the stratosphere, a high atmospheric layer that absorbs energetic sunlight. Changes in ultraviolet output can therefore alter stratospheric temperatures, influencing circulation patterns that sometimes extend downward into the atmosphere below and affect weather systems. Another connection arrives from deep space. During solar minimum, the sun's magnetic field becomes weaker and more orderly. As a result, cosmic rays, high energy particles originating far beyond our solar system, penetrate the heliosphere more easily and reach Earth in greater numbers. Some researchers have proposed that these variations influence cloud formation by affecting microscopic particles around which water droplets develop. The idea remains controversial. Evidence supporting the connection exists, yet important questions remain unresolved. Experiments, including studies conducted through the Cloud Project at the European Organization for Nuclear Research, continue examining how cosmic rays interact with atmospheric processes and whether those interactions significantly affect cloud cover. Patterns in living systems have also attracted attention. Researchers have proposed links between the solar cycle and phenomena ranging from influenza outbreaks to fluctuations in animal populations and tree growth in northern forests. Some correlations appear intriguing, others fade under closer examination. Establishing true cause and effect is extraordinarily difficult because biological and environmental systems respond to countless overlapping influences. What remains beyond dispute is the larger reality. The Sun defines Earth's habitability envelope. Over approximately 4,500,000,000 years, its luminosity has increased by about 30%. Early in Earth's history, our star was substantially dimmer than it is today. By simple calculations, the young planet should have been frozen beneath global ice, but it was not. This contradiction, known as the faint young sun paradox, was articulated by Carl Sagan and George Mullen in 1972. Decades later, it remains one of planetary science's deepest unanswered questions, reminding us that even after centuries of study, the star sustaining every moment of life on Earth still holds profound mysteries. When we spend enough time studying the Sun, a larger question naturally emerges. Is our star behaving according to rules shared across the galaxy, or are the rhythms we observe somehow unique? To answer that, astronomers have spent decades looking beyond the solar system and watching other stars live through their own magnetic cycles. One of the most influential efforts began during the 1960s. At Mount Wilson Observatory, astronomer Olin Wilson launched what became known as the H and K project. Rather than counting sunspots, researchers monitored calcium emission lines within stellar atmospheres. These spectral signatures act as indicators of magnetic activity. By measuring them repeatedly over many years, astronomers could track long-term changes in distant stars, much as we track solar activity on our own Sunday. Patterns soon emerged. Many stars resembling the Sun displayed recurring cycles. Their magnetic activity rose and fell over time, producing rhythms remarkably similar to the familiar 11-year solar cycle. Yet the details varied considerably. Some stars completed a cycle in roughly 7 years. Others required 16 years or more. Certain stars exhibited irregular fluctuations, while others entered prolonged periods of unusually weak activity, resembling the grand minima discussed earlier. One example attracted particular attention. A solar analog known as Hotel Delta 4915, located approximately 56 light-years from Earth, exhibits a well-defined activity cycle that closely resembles our own star's behavior. Observations suggest that the mechanisms shaping the sun may operate across many similar stars throughout the galaxy. But stellar activity does not remain constant from one type of star to another. More massive stars often rotate faster than the Sunday. Rapid rotation strengthens magnetic dynamos, producing more vigorous magnetic fields and more frequent energetic eruptions. As a result, these stars commonly experience stronger flare activity than anything observed from our own Sunday. The contrast becomes even greater among red dwarf stars. These small, cool stars are the most common stellar population in the Milky Way. Despite their modest size, many generate astonishing magnetic outbursts. Some release superflares with energies far exceeding those recorded during modern solar observations. Evidence for such events expanded dramatically through observations from the Kepler Space Telescope. Analysis of Kepler data revealed thousands of solar-type stars producing flares between 10 and 10,000 times more energetic than the strongest events documented in recorded solar history. The frequency of these superflares decreases sharply among older, slowly rotating stars that most closely resemble the Sunday, but it does not disappear entirely. That finding carries profound implications. A planet orbiting within the habitable zone of an active red dwarf may receive suitable warmth for liquid water, while simultaneously enduring intense ultraviolet and X-ray radiation. Over geological timescales, repeated flare activity could erode atmospheres and transform surface environments. Seen against that broader galactic backdrop, the Sun appears less remarkable for its power than for its restraint. It remains active enough to sustain a dynamic planetary system, yet stable enough to avoid the relentless violence seen around many other stars. You can begin to appreciate how unusual that balance may be. Complex life did not emerge beside a perfectly calm star. It emerged beside one whose long rhythms, despite their fluctuations, allowed billions of years of continuity in which biology could slowly unfold. Every living thing on Earth exists during a particular chapter of the Sun's life. Our star feels permanent because human history occupies only a tiny fraction of its existence, yet the Sun is changing continuously, following an evolutionary path shared by countless stars throughout the galaxy. Today, the Sun is approximately 4,600,000,000 years old. It is in what astronomers call the main sequence phase, the long period during which hydrogen in the core is fused into helium. This stage provides remarkable stability. For billions of years, the balance between gravity pulling inward and energy pushing outward has kept the Sun shining with extraordinary consistency. But that balance slowly evolves. With each passing era, hydrogen becomes less abundant in the core. As the internal structure adjusts, the Sun gradually grows brighter. Over the next 1 billion years, its luminosity is expected to increase by roughly 10%. That change may sound modest, yet, on planetary timescales, it is profound. Earth will feel the difference. Higher temperatures will accelerate evaporation and alter atmospheric chemistry. Oceans will gradually lose water to space. Long before the Sun reaches old age, conditions at the surface are expected to become hostile to complex life. Liquid water, the foundation of Earth's biosphere, will eventually become unsustainable across much of the planet. Yet the Sun itself will continue. Approximately 5 billion years from now, the hydrogen fuel at the center will be largely exhausted. Fusion will continue in a shell surrounding the core, causing the outer layers to expand dramatically. The Sun will transform into a red giant, swelling to perhaps 200 times its current radius. The inner solar system will be reshaped. Mercury will almost certainly disappear within the expanding stellar envelope. Venus faces the same fate. Earth's ultimate survival remains uncertain, but many models suggest our planet may also be engulfed as the sun reaches its maximum size. But even this giant phase is temporary. Over roughly 1 to 2 billion years, the outer layers will become increasingly unstable and drift away into space. These expanding shells of gas will form a planetary nebula, a glowing cloud illuminated by the exposed stellar core. Planetary nebulae rank among the most beautiful structures observed in astronomy, displaying intricate patterns of color and light across interstellar distances. At the center, a remnant remains. The surviving core becomes a white dwarf, an object roughly the size of Earth containing much of the Sun's former mass compressed into an extraordinarily dense sphere. Initially, it will be intensely hot. Then it will cool slowly across billions of years. One fate will never occur. The Sun lacks the mass required for a supernova explosion. Only stars at least several times more massive can end in that violent manner. Our star's conclusion is gentler, though its departing gases will enrich surrounding space with carbon, nitrogen, oxygen, and other elements produced during its lifetime. That realization brings us back to ourselves. The carbon within your cells, the oxygen you breathe, and the calcium within your bones were not created by the Sunday. Those atoms were forged in older stars that lived and died before our solar system existed. When the Sun formed 4,600,000,000 years ago, it inherited their material. Earth inherited it as well. In a very literal sense, the history of ancient stars continues through every living thing beneath the sunlight of today. A staircase is an unusual way to explore a star, yet that is precisely the path being followed today. Rather than rushing directly toward its final observing position, Solar Orbiter is gradually climbing above the plane of the solar system, using repeated encounters with Venus to reshape its orbit step by step. Each flyby changes the view. The mission's designers sometimes describe this approach as a stairway to heaven strategy. Every gravity assist from Venus gently tilts the spacecraft farther from the solar equator. The process is slow because changing orbital inclination around the Sun requires enormous amounts of energy. By borrowing momentum from a planet, Solar Orbiter can accomplish what no conventional propulsion system could achieve economically. The most important observations still lie ahead. In December of 2026, the spacecraft is expected to reach an inclination of approximately 24 degrees. By June of 2029, that angle should increase to roughly 33 degrees. From that elevated perspective, Solar Orbiter will finally gain a meaningful view of the Sun's polar regions, areas that have remained frustratingly difficult to observe from Earth. Those poles matter enormously. At 33 degrees inclination, the spacecraft should be able to observe approximately 60% of the polar region clearly. For the first time, scientists will watch the complete evolution of polar magnetic fields as solar cycle 26 develops. Current expectations place the peak of that cycle sometime during the middle of the 2030s. But observation alone is not the goal. Researchers want to test one of the most important ideas in solar physics. The Babcock-Leighton mechanism proposes that polar magnetic fields help determine the strength of the following solar cycle. Until now, much of that theory has rested on indirect evidence and limited viewing geometry. Solar Orbiter will provide direct measurements of polar field strength and allow scientists to compare those observations against the actual behavior of solar cycle 26 as it unfolds. The experiment will happen in real time. At the same moment, another spacecraft is exploring a completely different region of the Sunday. While Solar Orbiter climbs above the solar system and studies the poles, Parker's solar probe repeatedly dives into the corona itself. One mission looks from above, the other samples conditions from within. Together, they create something new. For the first time, scientists can connect observations of the surface, interior processes, magnetic fields, corona, and solar wind into a unified three-dimensional picture. Questions that once required separate missions and decades of interpretation can now be examined simultaneously. Ground-based astronomy is advancing as well. The Daniel K. Inouye Solar Telescope in Maui, Hawaii, began science operations in 2022. Equipped with a 4-meter mirror, the largest ever built for solar observation, it can resolve structures approximately 30 kilometers across, which is about 18.6 miles, on a star located 150 million kilometers away, which is about 93 million miles. The images are extraordinary. Convection cells, often called granules, cover the solar surface like a constantly shifting mosaic. Each spans roughly 1,000 kilometers, which is about 621 miles. Textbooks long depicted these structures through simplified illustrations. Now we can see them directly, revealing details of rising and sinking plasma that earlier generations of astronomers could only imagine. In that sense, Solar Orbiter is more than a mission. It marks the beginning of a new way of seeing the sun itself. There are years that become reference points, years that scientists return to when explaining how a cycle unfolded, how predictions succeeded or failed, and how a familiar system suddenly revealed new complexity. For solar physics, 2024 became one of those years. The momentum was visible early. During January, February, and March, sunspot activity continued climbing beyond revised forecasts. Researchers had already adjusted expectations upward, yet the sun kept exceeding them. Active regions appeared in greater numbers than many models anticipated. Daily observations increasingly suggested that solar cycle 25 was developing into something stronger than originally expected. Then came May. On May 10th and 11th, an extreme geomagnetic storm reached Earth. Classified at the highest operational category, Group 5, it became the strongest geomagnetic storm in 21 years. Auroras spread far beyond their usual latitudes. Across the southern United States and regions near the equator, skies briefly displayed colors normally reserved for polar locations. Millions looked upward. The response was immediate. Space weather forecasts became a topic of everyday conversation. Social media platforms filled with photographs from nearly every inhabited continent. Reports later indicated that the website of the National Oceanic and Atmospheric Administration Space Weather Prediction Center struggled under extraordinary traffic demand as people searched for forecasts and explanations. But the sun was not finished. Throughout the following months, activity remained elevated. During August of 2024, the monthly sunspot count reached approximately 216, the highest value observed in 23 years. The number reflected a level of magnetic activity that had become impossible to dismiss as a temporary fluctuation. Autumn brought another milestone. On October 3rd, the cycle produced an X9 flare, the most powerful flare observed during solar cycle 25 up to that point. Less than 2 weeks later, on October 15th, the National Aeronautics and Space Administration and the National Oceanic and Atmospheric Administration officially confirmed that solar maximum had arrived. The cycle's deeper transformation was also underway. Between October of 2024 and January of 2025, the sun's polar magnetic field reversal progressed toward completion. Observations from monitoring programs tracked the transition as the global magnetic structure reorganized itself. Later measurements provided additional confirmation that the reversal had indeed occurred. By March 22nd of 2025, Solar Orbiter achieved another historic milestone. The spacecraft returned the first direct images of the Sun's south pole, opening the high-latitude observing phase that researchers had awaited for years. New findings followed. During November of 2025, the first published analyses of Solar Orbiter's polar magnetic field measurements appeared in the Astrophysical Journal Letters, providing the earliest scientific results from this new vantage point. Taken individually, each event was significant. Together, they formed a portrait of an extraordinary period in solar history. More importantly, they changed public awareness. For a brief time, the solar cycle ceased to be an abstract graph known mainly to specialists. People saw its effects with their own eyes. The sun became tangible, immediate, and personal. An 11-year rhythm that had unfolded above humanity for centuries suddenly revealed itself across the entire world at once. Knowledge often advances in an unexpected way. The more clearly we see a phenomenon, the more sharply its unanswered questions come into focus. After centuries of observation and decades of spacecraft exploration, the sun is understood better than at any time in human history. Yet some of its most important mysteries remain unresolved. One of them surrounds the corona. The sun's visible surface is far cooler than its outer atmosphere. Logic suggests temperature should decrease as distance from the energy source increases. Instead, the corona reaches temperatures of millions of degrees. For more than 70 years, researchers have tried to explain this apparent contradiction. One leading idea proposes nanoflares, extremely small magnetic explosions occurring in enormous numbers throughout the corona. Another suggests wave heating, where magnetic waves transport energy upward and release it into the surrounding plasma. Evidence supports both possibilities, but no final answer exists. The solution may involve a combination of mechanisms acting simultaneously. It may involve processes that current theories only partially describe. Even now, one of the sun's most visible features remains incompletely understood. Prediction presents another challenge. Humanity has now observed 25 numbered solar cycles through systematic records. Despite this extensive history, scientists still cannot reliably forecast the strength of the next cycle with complete confidence. The polar field precursor method remains the most successful tool available. It uses magnetic conditions near the poles to estimate future activity. Yet Solar Cycle 25 exposed important limitations. Recent research suggests that random variations in sunspot tilt angles influence cycle strength in ways that cannot be fully anticipated. If those fluctuations arise from inherently chaotic processes inside the sun, then a portion of solar variability may resist precise prediction indefinitely. The uncertainty may reflect a fundamental property of the system itself. Another puzzle flows outward from the star. The fast solar wind has become increasingly well understood. The slow solar wind remains more elusive. Scientists continue investigating exactly where it originates within the corona and what physical processes accelerate it into interplanetary space. Parker's solar probe is gathering observations closer to the source than any previous spacecraft. But the mystery persists. Far deeper in time lies the faint young sun paradox. Geological evidence shows that liquid water existed on Earth during its earliest history. Yet, the young sun produced roughly 30% less energy than it does today. By current understanding, Earth should have been frozen across vast spans of time. Proposed explanations include stronger greenhouse warming, reduced planetary reflectivity, and additional internal heating mechanisms. None fully resolves the problem. Then there is the question many researchers approach cautiously. Could the sun produce a superflare? Observations of distant stars suggest the probability never reaches zero. Estimates indicate that a flare roughly 1,000 times more energetic than the Carrington event might occur on a sun like ours only once every few thousand years. Such events appear extremely uncommon among older, slowly rotating stars. Still, uncommon is not impossible. These uncertainties are not signs of failure. They are markers of an active frontier. Solar Orbiter, Parker Solar Probe, the Daniel K. Inouye Solar Telescope, and future missions exist because these questions remain unanswered. Each new observation narrows the possibilities. Each discovery transforms a mystery into a sharper, more precise mystery, carrying us farther into understanding while revealing how much remains to be learned. A child standing beside an ancient river, a philosopher walking beneath a classical sky, a navigator crossing an unfamiliar ocean, a scientist adjusting a telescope, and you watching the horizon at the end of an ordinary day have all shared one experience. Each looked toward the same star. Across recorded history, civilizations have given the sun different names and meanings. They built calendars around it. They worshipped it, measured it, feared it, and depended upon it. Yet the object itself remained the same. The dark spotted disk, noted by Chinese astronomers around 800 years before the Common Era, was our Sunday. The sun sketched by Galileo Galilei through an early telescope was our Sunday. The sun observed by Richard Carrington during the famous eruption of 1859 was our Sunday. The sun photographed from a new polar perspective by Solar Orbiter during March of 2025 is that very same star. The continuity is remarkable. What has changed is our ability to perceive it. Generation after generation added another layer of understanding. Observers who once saw unexplained lights in the sky now recognize the signatures of magnetic storms. Features that appeared random gradually revealed patterns. Cycles emerged, connections emerged, causes emerged. But for most of human history, those connections remained hidden. When winters grew harsher during periods of reduced solar activity, few suspected a link to changes unfolding on the Sunday. People attending frost fairs on the frozen River Thames did not know they were living during a grand solar minimum. Communities startled by brilliant auroral displays could not have imagined that the source of those lights lay 150 million kilometers away, which is about 93 million miles, on the surface of a star. Today, we understand far more. Knowledge does not alter the sunlight reaching your eyes. The photons behave exactly as they always have, yet understanding changes the story carried by that light. When you watch a sunset, you are seeing energy that spent an astonishing span of time inside the sun before beginning its final journey. A photon may require anywhere from roughly 10,000 to 170,000 years to work its way outward from the core through countless interactions with surrounding particles. Only after completing that long passage does it travel freely across space, reaching Earth about 8 minutes and 20 seconds later. The light feels different when you know that, and the sun itself feels different. It is easy to think of it as fixed because human lifetimes are brief, but the star above us is dynamic. It cycles through periods of greater and lesser activity. Its magnetic poles reverse. Its atmosphere erupts. Long patterns unfold across decades and centuries. Even broader rhythms may extend beyond the span of modern records. Yet at the center of this vast system lies a mystery that remains only partly revealed. The magnetic field driving these transformations is extraordinarily complex. Despite centuries of observation and decades of spaceflight, humanity has only recently gained a meaningful view of the regions where some of the most important pieces of that magnetic story begin. We are looking at the same star our ancestors saw, but for the first time, we are starting to see it whole. Take a slow breath and consider what is happening within your body at this moment. Oxygen moves through your lungs and into your blood. Iron atoms help transport that oxygen from cell to cell. Calcium provides structure to your bones. These materials feel ordinary because they have always been part of your experience. Yet their history is astonishing. The oxygen you are breathing was not created by the Sunday. The iron within your blood was not created by the Sunday. The calcium woven throughout your skeleton was not created by the Sunday. These elements originated in stars that lived and died long before our solar system existed. Their story stretches far back in time. Early generations of stars formed from the simple materials produced after the birth of the universe. Within their cores, nuclear fusion transformed lighter elements into heavier ones. As those stars aged, they manufactured oxygen, carbon, silicon, calcium, and many other ingredients necessary for planets and life. Some ended through powerful explosions that scattered their contents across interstellar space. The galaxy was enriched. Clouds of gas and dust gradually accumulated the products of countless stellar lives. Over immense spans of time, those materials mixed together and became part of new generations of stars. Our Sun emerged from one of those enriched clouds approximately 4,600,000,000 years ago. In that sense, the Sun has ancestors. It is a second generation star, perhaps even a third generation star. Embedded within it are trace amounts of elements forged by earlier stellar populations. The Sun inherited matter from stars it never encountered, carrying forward materials produced across a much older cosmic history. And so did Earth. The same cloud that formed the Sun also formed the planets, moons, asteroids, and comets of the solar system. The atoms that eventually became oceans, mountains, forests, animals, and human beings all originated from that shared reservoir of ancient stellar material. This is why a famous observation remains so powerful. Carl Sagan often said that we are star stuff. Physicist Brian Cox has remarked that the atoms in your left hand probably came from a different star than the atoms in your right hand. Both statements sound poetic. Both are also scientifically accurate descriptions of reality. But there is another layer to the story. Among the countless stars scattered through the Milky Way, this particular one illuminated this particular planet. For approximately 3,800,000,000 years, sunlight provided the energy needed for biological complexity to persist and deepen. Every ecosystem, every civilization, every language, every work of art, and every scientific discovery unfolded within that narrow band of conditions. Nothing we have discussed exists outside that context. The researchers monitoring Solar Cycle 25 from Boulder, Colorado, the engineers guiding spacecraft across millions of kilometers, which is about hundreds of thousands to millions of miles, and the astronomers interpreting streams of data are descendants of people who once stood beneath the same sky with far fewer answers. They saw lights in the darkness without knowing their nature. They watched the sun rise without understanding its age, composition, or history. Now we know more. Not everything, but enough to recognize something remarkable. When we study the sun, we are not examining a distant object unrelated to ourselves. We are tracing the history of the material from which we are made, and the star whose light allowed that material to become alive and aware. Long after any individual observation has faded into history, The process itself continues. Measurements end, missions conclude, generations pass. Yet the star at the center of our solar system remains engaged in the same immense cycle that has unfolded throughout its entire existence. Solar Cycle 25 is already beginning its descent from the extraordinary activity of 2024. Sunspot numbers will gradually decrease. Active regions will become less frequent. The next solar minimum, the lower activity phase between cycles, will likely arrive sometime during the early 2030s. After that, Solar Cycle 26 will emerge and strengthen. The pattern will continue. It has repeated for billions of years. Long before there were telescopes, satellites, continents in their present arrangement, or living creatures capable of observing the sky, the sun's magnetic field was rising, reversing, weakening, and rebuilding. The cycle predates every chapter of Earth's biological history, but our view of it is changing. By 2029, Solar Orbiter is expected to reach an inclination of approximately 33 degrees, providing unprecedented observations of the solar poles. During the years that follow, it will watch regions that remained largely hidden throughout the history of astronomy. Parker's solar probe will continue exploring the outer atmosphere from extraordinary proximity. The Daniel K. Inouye Solar Telescope will keep resolving magnetic structures and convection cells at scales once thought impossible to observe directly. New scientists are arriving as well. Students currently sitting in university classrooms may spend entire careers investigating questions that only recently became accessible. They will inherit instruments already transforming solar physics and will likely build new ones capable of probing even deeper into the sun's behavior. Some mysteries may yield. The mechanism responsible for heating the corona could become clear within this generation. The source of the slow solar wind may finally be identified. Researchers may discover whether the polar magnetic field truly contains the predictive information needed to forecast future cycles with confidence. Perhaps. The tools now exist. The answers do not yet. Meanwhile, the sun continues its work. Every second, approximately 600 million tons of hydrogen are converted into helium through nuclear fusion. This process began before Earth formed and will continue for roughly another 5 billion years. The scale is difficult to grasp because it exceeds every ordinary frame of reference. Even Earth's future unfolds within that larger timeline. At some point, likely within the next billion years, increasing solar luminosity will make the planet far less hospitable to life. Oceans will diminish, surface conditions will change profoundly. Yet 1 billion years is such an immense interval that the entire history of complex life, from the Cambrian explosion until today, could fit within it more than twice. For now, none of that is imminent. The star rises, it cycles, magnetic fields twist and reorganize, eruptions emerge and fade. Hidden polar regions slowly rotate into view before spacecraft built by a curious species determined to understand them. And somewhere beneath the night sky, another person looks upward and recognizes something their ancestors could not. The sunlight waiting beyond the horizon is more than illumination. It is a continuing flow of energy, magnetism, fusion, and history, arriving from a star still revealing its secrets, even now.